Hello, here we continue on with two-sample inference. In particular, we are going to look at some methods when the two samples are independent of each other. And the starting place here is that suppose we have two populations with respective means mu1 and mu2 and respective variances sigma 1 squared and sigma 2 squared. And really here we are interested in performing inference on mu1 minus mu2. And so let me give you an example. Let's scroll down to an example to motivate things. Here's an example on page 5 of the notes that deals with weight gain. Go ahead and take a moment, read this example. Pause your recorder and read, or your video, and read this example. Okay, so after you have read this example, I want us to first identify the parameters of interest. There's actually two of them here. Notice we have two populations. One is all babies that would use Gibbs food, and the other is all babies that would use the competitor's food. And the thing that is being observed on each of the samples from those respective populations is the weight gain, and then the weight gains were averaged and the standard deviation was computed for the respective samples. But anyway, there's two parameters here, mu1, which would be the mean weight gain, for all babies who eat Gibbs food. Okay, not just those not just the 45, but all babies that would eat Gibbs food. Okay, and then mu2 is another mean, but it's a population mean for the second population. So I'm going to use some ditto marks here. It would be the mean weight gain for all babies who eat the competitors. Okay, and let me say the competitor's food, and I really should say the Gibbs food up here. And so we want to, in terms of comparing the two populations, there's several ways to do that. A straightforward way to compare the two populations, while it's not a perfect way to do it, but is to look at the difference of the two population means. And so here we want to perform inference on mu1 minus mu2, because if we know something about mu1 minus mu2, then that can tell us how mu1 and mu2 compare. That is, if mu1 is bigger than mu2, we would expect the difference to be positive. If mu1 was less than mu2, we would expect the difference would have to be negative. Okay, so let's go back to the development of our statistical methods here with that in mind. But the big picture right now is for us that we want to do inference on the difference of two population means. Okay, a natural point estimator for mu1 minus mu2 is the difference of the two sample means, which is given by this expression here. All right, so we're going to use that as our point estimator. We're going to use that as our starting point to develop an inferential technique for mu1 minus mu2. Okay, so a little bit about the difference of the two sample means. First, the sampling distribution of y1 bar minus y2 bar is, well, it's normal if the populations are normally distributed. That is, if the two populations I'm sampling from are normally distributed. B, it's approximately normal. for large samples for any two populations from which we sample, and this is really a result of the central limit theorem. So basically, the difference of two sample means, and the sample means if they come from independent samples, is going to be normal if my populations are normal that I'm sampling from, or it's going to be approximately normal if my sample sizes are large. Okay. Also, so that tells us something about the shape of the distribution of the difference of the sample means. The average of the sample means, the symbol we have for that is mu sub y1 bar minus y2 bar. It turns out the average of that is mu1 minus mu2. So on the average, the estimate is equal to the parameter it is trying to estimate. Also, the standard deviation for the difference of the sample means is given by this expression here, the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Okay, so with that in mind, we can come up with a statistic that will act as a pivot quantity for us to do inference, and I'll explain the idea of pivot quantity a little bit, or a little bit more here. If we represent here, we can say, hey, y1 minus y1 bar minus y2 bar minus, what I'm doing is I am standardizing. I'm going to standardize the difference of the sample means. So you remember, to standardize something, you take that something, you subtract off its mean, and then you divide by its standard deviation. So I'm going to divide this by sigma 1 squared over n1 plus sigma 2 squared over n2. Okay, now this is a standardized normal variable if we are under setting A, and it's a standardized approximate normal variable if we're under setting B. Well, so what does that tell us? If we standardize something that is normal or that is approximately normal, then we get that new standardized quantity follows a standard normal distribution. So this ratio is standard normal. And just to be clear here, that's if both populations are normal. Or I could say that this ratio here is approximately standard normal if both n1 and n2 are large or sufficiently large. We're going to use the same rule of thumb that 30 is our threshold there. Now I want us to think about this quantity as an important quantity. It looks similar to the kind of quantities we saw earlier. If you recall, in an earlier module, we had standardized x bar, and when we standardized it, we had this sort of thing here, and that acted as our basis to form a test statistic for mu and also to form a confidence interval for mu. Okay, so we're doing a similar thing here, except now our estimator is the difference of the sample means, and so we get this resulting ratio here, which is called a pivot quantity. Your book may use that sort of language. A pivot quantity is basically a function of a estimator and the parameters whose distribution does not depend upon the parameters, and that's what we have here. This is that function, and these distributions here do not depend upon mu1 or mu2. Okay, so moving along here, the kinds of hypotheses that we could test in this setting would be a left tail, two tail, and a right tail test. And let's start off with, say, the right tail test. That we're checking to see, is mu1 minus mu2, is it bigger than some value d naught? Now typically d naught is 0, and so if d naught is 0, then this alternative looks like mu1 is bigger than mu2. Okay, if d naught is 0. And that's a common alternative hypothesis. Is the first mean bigger than the second mean? Okay. Now, having d naught here instead of just making that 0 all the time allows for more flexibility in our testing scheme. So we're here, this particular alternative hypothesis is asking the question, do we have statistical evidence to conclude that mu1 is bigger than mu2 by at least d naught units? Okay, that's a right tail test. Left tail test would be mu1 minus mu2 is less than in the alternative, and then now the two tail test is that mu1 minus mu2 is not equal to d naught in the alternative. Okay, so moving along here, we're going to look at kind of a starting case, inference for the difference of the population means when the two population variances are known. All right, the assumptions here are that we have 1, independent random samples, 2, that we have normal populations, I should say, not just a single population, but both of our populations are normal, or we have quote-unquote large samples. And then thirdly here, that sigma 1 squared and sigma 2 squared, that is the variances of the underlying population, are known. In this scenario, our test statistic is going to look like, well, this pivot quantity, this ratio, this standardized quantity that we saw earlier, except I've replaced mu1 minus mu2 with d naught. And this right here is actually mu1 minus mu2 under the null hypothesis. So for example, if you look at the two-tailed test here, mu1 minus mu2 is d naught under the null. Under the left-tailed and right-tailed tests, it's part of the null hypotheses, and it's on that threshold, and we choose that value that's going to give us the most conservative test against making a type 1 error. That's why we choose it at the threshold. But, let's see here, kind of zoomed in, didn't mean to. That's our test statistic to do either one of these 3 tests here. Okay, moving along, the confidence interval seems quite intuitive. It's the point estimator plus or minus a z percentile times the standard deviation of my point estimator. And we've had this sort of thing in a prior module. The distribution of my test statistic, if I'm going back to this test statistic, is as follows. If the two populations are normal, then Z is distributed standard normal, and if at least one population is not normal, but both N1 and N2 are large, then my Z statistic is approximately standard normal. And so what I have here is a null distribution for this particular test statistic. Now, the problem with this particular test statistic is that it assumes that we know that we can plug in a value there. That assumes we know the standard deviations for both populations, and that's rarely the case. If you're doing inference on a population mean, you're not going to know its population standard deviation, and so we're not going to know these values, so we need another approach here, and that's what this next scenario deals with. The more practical scenario, let's see here, the more practical scenario when sigma 1 and sigma 2 are unknown. All right, and this is in the previous notes, this is when we made a transition from a quote-unquote z-test on a single population mean to a t-test on a single population mean. Now, in this scenario here, we have two types of statistics that we're going to consider. One is when the sample sizes are large, that is, N1 is bigger than 30 and N2 is bigger than 30. And the other scenario is when the sample sizes are small. That is, N1 is less than 30, or we just need one of them to be less than 30, okay? N1 or N2 is small. But that the two samples come from normal or near normal populations. Okay, this is the two kinds of scenarios we're going to consider here. Scenario 1, the large sample scenario. The conditions or the assumptions for this scenario to be appropriate are that I have independent random samples, that I have large samples. Again, I may be making too big of a deal by having us write this so often, but both sample sizes are large, bigger than 30. And then the variances do not have to be known. That is, they're unknown, and that's more practical than where we were. And here, I've got, maybe I should be more clear here, is that the variances are allowed to be different. That is, the variances of the two populations, they may be different. They don't have to be the same. It turns out when we, as we look at another method, that will be a requirement that we have the same variances. But for us, right now, we're not going to assume that. The test statistic in this situation is given here. And if you look at that, that is the same as this, except we have replaced, seems a very natural thing to do, we have replaced our population variances with the sample variances. Okay? Alright, so the corresponding confidence interval here, you probably could write it down without my help, but it's the difference of the sample means plus or minus the standard percentile times the square root of S1 squared over N1 plus S2 squared over N2. Now, this test statistic here, what is its distribution? It is approximately standard normal under the null hypothesis, and that's by the central limit theorem. Okay, the central limit theorem is driving the normality of the difference of the sample means, and hence this test statistic's null distribution. Now, a problem with this kind of statistic is that if N1 and N2 are not both large enough, you might think, well, shouldn't this ratio then follow a t distribution? It turns out it doesn't. So we need another way we want to involve the t distribution, but we have to make an extra condition in order to do so. So let's go here to scenario 2, one where we have small samples and what I'm saying is equal variances. The conditions or the assumptions in this scenario are that I have independent random samples, that my normal populations are in fact reasonable, and that the normal population's assumption is reasonable. The two population variances are unknown, but I am assuming that they are equal. So I'm going to assume, while I don't know them, that they are equal. Now, later on, we will test this assumption in a formal, what's called a formal F-test. But for now, we're just going to we're just going to look at the sample variances, and if the sample variances are pretty close, a rule of thumb is in this is if one is not twice the other uh, in regards to their standard deviations, really, then you can go forward with it's okay to go forward with the equal variance assumption. All right, so this common variance sigma squared is what we need to contend with, and if we do contend with that, we need to estimate the common variance, and this common variance is estimated, or really the common standard deviation is estimated with this thing called SP. This is called our pooled estimate of the common standard deviation. There's a pooled estimate there. Okay, and as a result, what we have here is a pooled test. And let me just make a note of that. This procedure under scenario A is called a pooled t-test. Okay. It's pooled in the sense that we are pooling our information together to estimate the common variance. It's pooled together through, if you look at this, and if you kind of think of, hey, this is this quantity times S1 squared plus this quantity times S2 squared. That's like a weighted average of the two sample variances. And so we're pooling the information together, and in doing so we have this certain kind of estimate. And it turns out that when we replace the common standard deviation sigma with its estimate SP, that this actually does have a t distribution. Okay, and so this is our test statistic here. Just to be clear, it's kind of redundant. I've got degrees of freedom there, but the distribution of this test statistic is what it's labeled here as a t, follows a t distribution, student's t distribution, and the degrees of freedom is n1 plus n2 minus 2. Okay, the pooled t-test. That's what this test statistic does for us. Now, a confidence interval for mu1 minus mu2 is given by this expression here. And you can see it's a similar structure. It's a point estimate plus or minus a percentile, in this case a t percentile, times this overall quantity here is the standard error, or an estimate of the standard deviation of this quantity under the assumption that the population variances are the same. So these are our two formulas here, a confidence interval formula and a hypothesis test statistic. Scenario 2 here, I'm still under the small sample scenario, but now I'm going to relax this assumption. What if the variances are different? What if the variances are different? Well, here's an approach that allows me to do an approximate test. And so I'm allowing everything else is the same under the assumption heading, but I'm allowing my variances to be potentially different. Okay, the test statistic here, using the notation of our book, is a t prime. It looks the same as actually the above z statistic that we had a page or two above. But here we're not assuming that we don't have large samples, but we are assuming that we have normal populations. Now this quantity here has degrees of freedom that's given by this kind of crazy ratio there. It involves C, and C is given in this expression here, and without going into too much detail within the lecture on what motivates those, the big idea is that these quantities approximate the degrees of freedom, or it allows to give us a t distribution that approximates the true distribution of this ratio, which we don't have a good closed form for. So thinking about what is t prime here, t prime, yeah, it's that ratio, and it's distributed approximately, so that's where I have the dot on top, approximately t with the above degrees of freedom. That is, here's the above degrees of freedom. Okay, if you look in your book, they will call this technique the Welch-Satterthwaite t-test. And also, I should tell you, with this quantity here, we want to round down if this is not an integer. Okay, round down if it's not an integer. Okay, Welch's t-test for the small sample but unequal variance case. All right, so let's come back to this example. Now, after you've read through this, think about which of the procedures would we use. Okay, we're not going to use the very first procedure. We already talked about it being unpractical because it requires knowledge of the two standard deviations, or of the two population standard deviations. Do we have a large sample here? Well, yeah, we kind of do. Or it's, we've exceeded that 30 threshold that we've kind of drawn a line in the sand as a rule of thumb. The two sample sizes are large enough for us to use this large sample z-test to compare the two population means. Okay, so we're going to apply that. But I guess before we apply that, though, let's actually identify our hypotheses. So recall, as setting up a hypothesis test, it is usually easier to identify the alternative hypothesis first. Okay, and that corresponds to the question that is being asked. The question that's being asked here is, can we conclude that babies using the Gibbs brand gained less weight? Okay, that is, can we conclude that mu1 is less than mu2? That's the claim we want to test. By the way, that's the same as checking to see if mu1 minus mu2 is negative. If that is the alternative hypothesis, then the null hypothesis would be that mu1 is bigger than or equal to mu2, or equivalently that the difference is bigger than or equal to 0. But this is the claim we want to test, and we're going to do that with our z test statistic here. Okay, so I'm going to write that out here. We use this z test statistic because both sample sizes are large. And I didn't have to check or consider the normality or lack thereof of the two populations because the central limit theorem is kicking in for us here. but because of both sample sizes, that is N1 is 45, N2 is 40, those are large, or they are large enough. Okay, that is my test statistic there. The observed value of our test statistic, then we can use that to make a decision. We can use the p-value to make a decision. The observed test statistic would be as follows. I'm going to say z observed here. What are my sample means? Well, the subscript 1 corresponds to Gibbs. The sample mean for Gibbs was 7.5, and the sample mean for the competitors, sample mean weight gain was 9.3 pounds. So I've got 7.3 minus, I'm sorry, 7.5, is that right? 7.5 minus 9.3. Now clearly the difference of the two sample means is negative, but I want to know, is that enough? Is there enough evidence within this disparity to conclude that the population means, the difference of the population means, are also negative in this way? So I'm running that through the test here. That's the whole point of the test. Take the difference of the sample means, subtract off d naught. What's d naught here? Well, it's 0. The difference, the null hypothesized difference of mu1 and mu2 is 0 in this situation. Then I'm going to divide by the standard deviation. Here I've got 2.0 squared, that's S1 squared, and then I've got 45 is my sample size for sample 1, and then 2.9 squared over 40 there in the denominator. If you do the arithmetic here, you should get negative 3.29. Okay, negative 3.29. Now, that would give us insight into the p-value. The question is this a rare test statistic under the assumption the null is true? The p-value speaks to that rarity, and so the probability here of z being less than or equal to negative 3.29, that's what I'm going to look at for my p-value. If you look on the z chart, you should get something, depending on which one you use. The one I used showed me 0.0005. And so my decision would be we would reject H naught and accept H1. Okay? And so the interpretation is we would say we have, let me fix this. We have sufficient statistical evidence to conclude that mu1 is less than mu2. That is, the average weight gain for babies under Gibbs is less than that under the competitor's brand. Now I used symbols here, and I feel okay doing that and not writing out the phrase that corresponds to mu1 and mu2. I feel okay doing that because I defined mu1 and mu2 up front. if I had to find that, then I would want to write out in words that we have sufficient statistical evidence to conclude that the average weight gain under Gibbs is less than the average weight gain under the competitor's food. Okay, so that is a hypothesis test comparing the difference, or the comparing two means here. I want to also, I've got a little space in here, is to compute a corresponding confidence interval. And so if I'm looking for a confidence interval here, let's just do, say, a 95% confidence interval. We'll want a 95% confidence interval for mu1 minus mu2. What are some plausible values for the difference of those two population means? Well, I take the formula, again, y1 bar minus y2 bar plus or minus a z percentile times the square root, that square root term there that we have already dealt with. Okay. So I take the difference of the sample, just to plug in here, I'm going to have 7.5 minus 9.3 plus or minus, for a 95% confidence interval, this is going to be, the z-score is 1.96. We've done that sort of thing before. And this is going to be over 2 squared over 45 plus 2.9 squared over 40. Okay, if we do that, then we get negative 1.8. That's our point estimate for the difference of the population means. We got to add and subtract some stuff to it to get the margin of error. Margin of error, the turns out to be 1.07. So let's see here. So add and subtract that to my point estimate, and you get a lower bound of negative 2.87 and an upper bound of, still going to be negative 0.73. And so the way we would interpret this, if you look at it, it corresponds to the alternative hypothesis, right? It's saying all the plausible values, we're 95% confident the difference of mu1 and mu2 is in between these two values. That is, we're 95% confident that the difference is negative. That corresponds to this alternative hypothesis here. Okay, let's write out, just to be complete, the interpretation of this interval here. We would say we are 95% confident that the average weight gain for all babies using Gibbs is less than the average weight gain let's see, I missed the word gain in here. The average weight gain for all babies using the competitors it's less than that quantity by at least 0.73 pounds, but by, I forgot the word at least, by at least 0.73 pounds, but by at most by at most 2.87 pounds. Okay. You could have worded it another way. You could have said we're 95% confident that the average weight gain for babies under the competitor's food is greater than that of Gibbs by at least 0.73 pounds, but by at most 2.87 pounds. Okay, so this concludes the major methods on comparing two population means from independent samples.